each and every atom behaves like a scattering center for the incident beam, and it scatters. Right? Now, we are saying that the diffraction is telling us about the orientation of planes. We are saying atoms are behaving as scattering centers, and diffraction, which is the same scattering coming from these atoms, are telling us about the geometry of the cell, about the about the interplanar spacings, about the angles at which the planes are oriented within a crystal. Right? How this is happening? Why they are different things are telling us? It is because of the structure factor. And just like we are saying the packing fraction is different from cubic, from BCC, from FCC, and from for other crystal system. In the same way, the structure factor depends upon the how much scattering centers are coming in front of the beam. So if the plane is, for example, 100, and the beam is incident upon that plane, then it is diffracted. It is to diffract from a different bunch of atoms. If I say it is 110 plane, one was like this, the other is like this, for example. The other is like this, right? So different bunches of atom. By bunch I mean the plane is actually a bunch of atoms. When different bunches of atoms confront the beam, it will be diffracted differently. Right? It will be diffracted differently. Secondly, if the plane is not satisfying the Bragg's law, no intensity will come from there. Intensity is coming from there. The beam interacts with that, but that beam, that wave is not interfering constructively with the other beams. And that is why you have no intensity here. So the diffraction, the diffracted beams, the scattering are occurring at 2 theta values from here to here. But they are not satisfying the Bragg's law. And they are not interfering constructively after diffraction. And that is why you have no intensity there. If you have less intensity and more intensity, it again depends upon this structure factor. If it's the individual factor of the individual atoms, and 2 pi I h mu1 h u1 k v j and l w I The IJK on the pakar dega na, right? But the subscript will represent that number. So HKL is important, right? The HK. So if you spread this equation, it will be cos theta plus iota sin theta, right? And when the value of both contribution is 0, it will give you 1. So the structure factor will be Fi, right? So it will wholly solely depend upon the atoms. If cos theta plus I sin theta are giving you different values, for example -1, right? Then it will be come down and it will divide the structure factor. Similarly, if it gives you higher value or lower value, then that is affecting the structure factor. So the structure factor is dictated by the HKL values. Listen to this carefully. For certain HKL value, it will give you 0 structure factor. When the structure factor is 0, it will not give you any intensity. And if you go into the details, if H is 0, K is 0, and L is non-zero, and it gives you some value, right? Then H even, K even, L odd. H, K, L all even will give you one sort of value. H, K, L all even. 0, 0, 0, 2, 2, 2, 4, 4, 4, 6, 6, 6, 8, 8, 8, all will give you one sort of value. H, K, L, all odd. H, K, L, all odd. 131 is all odd. 111 is all odd. 333 is all odd. 131 all odd. It will give you another value. If that value is none, overall structure factor becomes non-zero, then there will be some intensity. But if the overall outcome of the specific values of HKL is 0 for the structure factor, it gives you 0 structure factor, there will be no intensity. And from there, people define the symmetry. That this is 0, 0, 0, and this is 2, 0, 0, then where did it go? 1, 0, 0. Right? Similarly, from here, if this peak is 1, 0, 0, right? And 2, 0, 0, then where is 1, 0, 0? Where are other values? When they are missing, this means that they are giving 0 contribution to the structure factor, and that is why 1, 0, 0 is not there. Because the contribution from here is giving, and these are called the forbidden reflections. Remember this. The forbidden reflections are those for whose HKL values the structure factor gives zero contribution, and that reflection will be forbidden. If you are wearing this, then common sense says that you should have 100, 010, 001, then 110, then 101, then 011. And in this 11 category, how many diffraction peaks will be there? And when you reach up to 999 HKL, you will have millions of HKL indices, but that is not occurring because of that structure factor. So the structure factor dictates whether a particular reflection will be there or not. And if it is there, for example, an electron diffraction, an electron is scattered from here, but scattered from somewhere else and gives you intensity here, which is not expected, then people call it double diffraction, which is unusual, but it happens. Now, if H plus 2K is odd, that is L is odd, and FHKL is 0, right? So you will have no reflection where the H plus 2K is odd. Similarly, its value is 4Fi square, if you remember, Fi, right? 4Fi square, when H plus 2K is equal to 3n and L is even. This means that L odd is not allowed and L even is allowed. So all the reflection with L odd will be missing from your XRD pattern, right? Similarly, 3f square and f square are various choices of HKL. So their combination as well as their individuality. Individually they are odd or even, that contributes. Collectively they are odd and even, and that give rise to various symmetry conditions. That if that symmetry is not there, then this means we will go to a little bit lower symmetry. Lower means less symmetric. Higher symmetry cubic. The highest symmetry sphere. Less symmetry than cube is tetragonal. Then within tetragonal, if you have simple primitive cell, non-body centered and different type of centering, face centering, then obviously when you increase the number of wings, the symmetry will become complicated, right? So this is the structure factor where J is the number of atoms and Fj is the scattering factor of atom J, right? The scattering factor of atom J, but then we are saying it is reflecting the specific plane. So the concept of plane comes from HKL, and HKL contributes to your diffraction spot. The denser the atom, denser means more electron around the nucleus, for example. The more confrontation it will offer to the beam. So when you are doing metallic samples, then you need the X-ray beam with a specific suitable energy so that it is not absorbed completely and give you the diffracted beam. So that is why different sources of X-ray, copper, molybdenum, and many others are used for various samples. Selection rules for reflections in cubic crystals. As I told you that when we start from there, and then the h square plus k square plus l square gives you 1, 2, 3 up to 16. Simple cubic allowed. BCC, when it is odd, not allowed. When it is even, they are allowed. So when you look into specific reflections, from here you guess about the specific structure from which the diffraction pattern is coming. FCC, 1 and 2 are both not allowed. Only the 4 is allowed, right? When it is 4, H plus K plus L equal to even, then they are allowed. But they, in the case of 2, they are not allowed. FCC. So it lowers the symmetry. Lowers the symmetry. Increasing the symmetry is actually lowering of the symmetry. More symmetric, right? Less symmetric when you increase the number of atoms in the unit cell. 2 theta angles. They used to scatter the X-ray beam from the sample, and there used to be a plotter, manual plotter type thing, and that used to plot the intensity of peaks. There used to be tractor type printers. So they used to get the peaks at these angles. Now how they used to transform these? So soda base 5-step program for determining crystal structures from only angles. Only from angles he used to determine the structure. How? Step 1, start with 2 theta values and generate a set of sine square theta values. And this is the sine square theta values for these values of 2 theta. Look at this, how intelligent those people work. From only angles, he is deriving the structure. Then, when you did that, the second step is normalize the sine square theta values by generating sine square n theta over sine square 1. Right? Divide all by 0.143. So he got 1.34 and like that values. In the third step, clear fractions from normalized column. What he did? By clearing fraction, he got 1, 3. He multiplied by 3 to get to the closest whole numbers. Right? When you multiply 1.34 by 3, it will give you 4. Similarly, 2.67 will give you 8. And he got these values. Speculate now. The scale values that f expressed as h square plus k square plus l square would generate the sequence of a clear fraction column 3, 1, 1, 1, h square plus k square plus l square. 4, 2, 0, 0, h square plus k square plus l square, h is 2. And in this way, he got these numbers. And these are the HQL indices and planes. Then compute for each theta the value of sine square theta over scale on the basis of the assumed scale. If each entry in this column is identical, then the entire process is validated. Paltan, if you remember from your old mathematics, that if you can revise the process and it gives you the same value, this means your calculation is correct. And you determined the Miller indices only from angles by this method. I am just giving you a visit of how we compare the real and reciprocal lattice. Here, the vectors are bigger, longer, there are shorter. This is 100 plane. Look into this. Students usually get confused which plane is which, and there will be a number of questions from this in the exam as well. There will not be these. There will be some complicated ones. But look into this, right? 100 intersects x-axis at 1A and is parallel to the y and z-axis. Then 110 intersects x and y axes at 1, and parallel to z-axis. Right? Intersects. This is x and this is y. It's before intersecting and it is parallel to the z-axis. Then 200. 200, listen to axis at half and parallel to the other two. 1 bar 00. So it is intersecting the x-axis at -1, -a, and gives you. Yesterday I also told you about the JCPDS card. So this is the old patient JCPDS, Giant Committee for Powder Diffraction Standards, right? Gold crystal system, cubic, lattice parameter A. When B, C are not there, this means it is cubic. Alpha, beta, gamma are not there. This means they are all 90. Then who did it? Reference elements of methodology 17. And the other is Winchell, right? And how the material was prepared, right? They give the material, then there, look, B and intensity, this intensity is I over I naught. I over I naught. They haven't got exactly 150 or like that, but they divided the maximum on the maximum intensity, and 100% was the highest, and then the lower values came from there. HKL are there, and they have not given the 2 theta values, but they usually give 2 theta values as well. And that wavelength must be there, whether you use copper or molybdenum or other. The modern way of representing things is not visible. That is why I missed this. I was doing it in hurry. So they give the diffraction pattern as well. The modern computerized programs are giving you, this is the X-ray diffraction, and you ask for the electron diffraction, they will give you electron diffraction as well. And here you see, is it B? Intensity HKL, B, intensity HKL, B, intensity HKL. So all the peaks are given, and the space group and all information is given there, but I can't see it. Now, look at this. How people study the phase evolution. You don't see a good peak here. But here you see something, and when you go here, it increases. So one phase is increasing in intensity. Increasing in intensity means its fraction is increasing. More crystal of this type are forming. If a peak was there and its intensity decreased, then you say with temperature this particular phase transformed into some other phase or dissolved into an amorphous material. But if you look here, its peak is not present here. This corresponding to a phase, this peak. So if it is down there, it is at A is the received sample, and A is the received sample, 800, this is 800, this is not 000, right? So when you heat the sample at 800 and this peak is absent, much decreased in intensity. So you say, not at 800, at some temperature below 800, this phase dissolved or transformed into other phases. If nothing is happening instead of that phase, this means that the phase dissolved. If at the cost of that particular phase, the peaks due to another phase increased, this means that phase transformed into another phase with temperature, right? If the material is glassy, it is like this. These are the same patterns, but I squeeze this and I blow that up, and you see how many spikes and things like that. So you organize the data into a presentable manner, but you must not conceal any information which was visible. So if you are playing, beats are not hidden. They are not they are the same orthorhombic structure. It is pure sodium aerobate, and that is also pure sodium aerobate at x equal to 0, right? But slight variations in intensity, the peaks are almost the same. There is some little bit difference between the two. The same crystal system in both, but the space group is different. And the crystallographers know it, that when they look into the X-ray diffraction pattern, they will tell you that it is PBMA and that is PBCM. And these are crystal symmetry things. PBCM. Here, I want to show you that look at this shoulder. When I was telling you that these shoulders are different peaks, but if you squeeze them, then you will not see different peaks there. And that's it. But now come screen sana dah ada internet jadi jalan Vamos dar uma olhada. Dá uma dita da nossa